All right. Happy Monday. We have 2 weeks left for the summer semester. So just your last push to get us through. And then we can enjoy for 2 weeks. And then we can either go away for the fall for an internship or a co-op, or maybe we continue to take classes. But no matter what, we at least get 2 weeks break. So before the break, let's try to push through these 2 weeks. All right. So we are going to continue our conversation on operating systems. Last class, we talked about introduction, right? Today, we are going to talk about a need for structure for an OS. And I'll talk about virtual machine. I'll talk about how we can create new processes. In order to increase the degree of multi-programming, you would need to do that. And then if time permits, we can make progress on our next lecture, which is about communication between processes. So I'll start with structure. So what is the motivation for the structure? Well, operating system is huge, right? And if it is especially general purpose operating system, Windows, Linux, Mac, OS, these operating systems tend to be very, very complex. They provide a lot of services. So for example, over here, we have a list of services. This is not a complete list, but essentially pointing out some important ones. So we have what? Program execution. Come on. Right, my Apple Pencil doesn't want to. Program execution. We have I/O operations, communication between processes. How do you allocate resources to different processes? Protection and security of what? Of good users from bad users and the operating system from the bad users. We have error detection. We are writing something to memory. We are going to check using parity codes or some other type of codes whether when we retrieve the data it's correct or not. And accounting information for all the things. For example, which process is using how much of the CPU resource, how much of the RAM, and so on. Right. So the OS is keeping track of a lot of things. Now, if you have something very, very complex, the first thing that you are going to think about is to modularize it, right? Like design this module and then this module. Divide and conquer policy is going to be your first choice, which is sort of the motivation for having a structure for an OS. Because it's complex, it's very large, we are going to need to divide it up into meaningful modules so that we can do a lot of things. We can troubleshoot in an easier manner, right? One aspect of the OS is not executing properly. We are going to fix that particular module, not everything. Suppose you're in a team, you're all working on designing this OS. Then you can say, all right, you guys are going to be the team that takes care of error detection. You guys are the team that takes care of resource allocation. You decide how we are going to schedule tasks on the CPU. Which cycles of the CPU are going to be for which process, and so on, right? What else? If you have a certain subroutine that you are writing for one, if it is modularized, then you can reuse it, right? So reusing increases, readability increases, troubleshooting is better. So there are lots of advantages of modularizing or providing a structure to your complex design. Exactly the same way as you guys did in COCO for VHDL. Behavioral codes, simple things, you could do it in one level. But as soon as you went for complex things, there was a need for a hierarchy, right? So then we said, all right, let's design the smaller modules, and then we'll put it all together in the top level. So that's what we did. We provided a structure to it, hence the name, structural modeling, right? So what are the types of structures? Early structures were monolithic, no structure at all, right? Hundreds and thousands of lines of code all in one module. There's no structure at all. And clearly that did not work well. So later ideas were based on organizing organizing layers or modules, and programming the interfaces between those OS services. So the first approach was layered structure, in which again you are isolating services into layers. But with a layered approach, it is different from a modular approach. In that modular approach is everything is a module. But in layers, there is a hierarchy that is strict, that is built in. So we'll take a look at how a layered structure would look like and some of the good or bad things in a layered approach. Some other modern approaches to an OS structure is microkernel, which is very popular. Essentially, it means that we'll try to make the kernel, the core of the OS, very, very small and push out all the other OS services to the user space. So that's one approach. Modular structures are like layered structures, but there is no strict hierarchy built into it. So no one service is sort of more important than the other. It is modular, but there's no hierarchy built into it. Or hybrid structures, which is a mix of many ideas, sort of taking the best of different layered approaches or modular approaches. So what we have here is a simple diagram showing how a layered operating system structure would look like. At each layer, you would have some service or services implemented. So all the way at the core here, you have your layer 0, which is the hardware. And as you're moving up from the hardware out, you are reaching close to the users, right? And between the users and the OS, you have that user interface that is implemented at layer N. And as you're going down, as you are going out of this core, you have one layer at which memory management is implemented, another layer at which CPU scheduling is implemented. Above that, virtual memory, and so on, right? So OS, large and complex, we need a good strategy to build them. The idea is to build them in layers. So it is somewhat a modular approach because it is still isolating services into modules, but those modules are one on top of each other, like layers of onion, right? As you peel it down, you go all the way down to the hardware. It is portable, which means that I could take these layers and port them onto a different hardware, right? So you can have a Windows operating system on x86 architecture, or you could have Windows operating system on a different architecture. So the portability is what is the benefit of layered architectures. Divide and conquer ideology. In order to make things simple, at one layer you only have a limited group, sort of limited services to worry about. So if that service gets disrupted, then you go looking for troubleshooting in that particular layer. Now, when you have a layered approach and you're building out, higher layers are going to be written in terms of lower layers. So layer 3 is going to be written in terms of 2, 1, and 0, and so on. Next, lower layers can hide details from higher layers. So when you have layer 2, it is going to hide the details from the higher layers. When you write layer 2, though, you will write it in terms of layer 1, layers below it. Now, it's a good news and bad news, right? If the good news is that there is inbuilt security in this approach, because layers above are not able to see layers below are not able to see what is coming above. They are completely blind as to how the upper layers are being implemented. The bad news is that if suppose you have a layer that needs the service of a layer above it, it's not going to be able to get that, right? So a service at a particular layer, it can only use services below. It cannot use a service above it. So that's sort of the bad news here with this layered approach. Let's see. So if you look at the brief structure here, where is the operating system services being implemented? So at the top over here, you have the users over here. They are interacting with the OS using shell, they're writing in commands, and the compilers are going over here. All of this is what? In the user space. And below that, we have the kernel space. The topmost layer in the kernel space, as close to the users as possible. What is that? It has all the services. Signals, terminal, input, output devices, file system support, CPU scheduling, virtual memory, main memory management. All of those services are being highlighted over here. Below that, you have things that are going to interact directly with the hardware. Controllers for keyboard, mouse, and so on. Device controllers, disks, tapes, memory controllers. And below that, of course, we have the hardware over here. So essentially what we are saying is there is a structure within the structure, right? This is sort of the general overall structure. What is that? Users, GUI, shell, whatever you have, and then services by OS, device drivers, controllers, and so on, hardware. Now, in the layer where you have services of the OS, we talked about how that is going to be layered as well, right? So it's a layered approach within a layered approach. All right, let's move on here. So CPU scheduling is something that we are going to talk about. In a little bit detail, we'll talk about what are the different algorithms you could have for CPU scheduling processes on a CPU. What should they be based on? Priority, length, the size of the process. So we'll take a look at a few variations there. We'll talk a little bit about file systems as well. We'll talk about how communication processes would communicate with each other, something that is not sort of indicated in this list. Right, so those are the topics that we are going to look at from now to the end of the semester. Next, virtual machine. You guys have done this, right? Especially if you are a Windows user, maybe you have not done it. Maybe you have not had a virtual machine or another OS that is hosted on your Windows operating system. But certainly if you are a Linux user or a Mac user, you might have at least thought of or actually implemented a dual OS, right? Dual boot or whatever you have. Just at least an environment to bring in your other operating systems. So I see that with Mac users a lot, where they need to use things that are Windows specific. So they would have Windows on their Mac OS. Boot camp is, yes, it's, so virtual machine is anything that is giving you an impression that you have two operating systems on one hardware, right? So anything that, so think about your laptop or your desktop. It has limited amount of hardware, right? Only, so you're going to have limitation on the number of cores, your main memory, and your network interface card. You're going to have limited physical resources. If you are sharing resources across two operating systems or more than that, then those are going to be called virtual machines. So it is, the idea is whether you are sharing those same physical resources between different OS environments or not. So if you're not doing that, then it's not a virtual machine. But if you are doing that, if your Windows is able to, identify something that you hooked up to the USB drive, then the Windows operating system, which could be an application that is running on your Mac OS, is using that physical resource, is using that. So that makes it a virtual machine. But we will have different variations. There's a type 1 virtual machine, there's a type 2, and we'll talk about that. There's a slight difference between the two types. So what is the virtual machine though? So here you have two virtual machines that are shown. Let me just highlight them here. So there is this guy over here, virtual machine 1, and then you have virtual machine 2, right? So these are guest operating systems. These are guest operating systems. Guest OS. Guest OS. And these are essentially running as applications on a computer. Right now it is based on x86 architecture, has limited resources, right? Some CPU, some main memory, some network interface card, some secondary hard disk. But these operating systems are able to time share those resources. And what is making it possible is this virtualization layer, right? So that virtualization layer is typically implemented through a hypervisor, and it depends on type 1 or type 2. But there is some software layer in there which is allowing virtual machines or guest operating systems to do a time sharing of the existing physical resources. So that's a hardware level abstraction, right? So virtualization layer over here is so virtual machines as long as you are in that virtual environment, you would think that these resources are just meant for this virtual machine. But the truth is that they are being time multiplexed between several virtual environments. So virtualization layer is actually giving you that extra level of indirection. It is decoupling the hardware and the OS. It is enforcing isolation between the two virtual environments over here, virtual machine 1 and 2. And it is essentially doing this, right? It's doing a time multiplex or physical hardware resources across the virtual machines. You could have 2, you could have more than 2. But again, the more and more you have, the time multiplexing is going to get bottlenecked, right? So what are the other ways you would do it? Mac users, how do you do it? You don't do it. Mac users in the room, how do you must have had at some point a need to have Windows on a Mac OS, right? How would you do it? Boot camp? Okay, VMware, yeah. You would use crossover, yeah. Parallel desktop software, yeah, there you go. So you guys have done it. That's exactly what we are talking about here. The hypervisor is that software layer that allows for that indirection. So it is an implementation of a virtualization layer. So software installed on the computer hardware creating the virtualization layer. It is going to act like a platform on which your virtual machine environments are created and on which they run. It is responsible to manage and share the physical resources between the virtual machines. So two types, right? Type 1 and type 2 for a hypervisor. One is bare metal hypervisor. So VMware Workstation falls in the category of type 2, but VMware ESXi falls under the category of type 1. So in type 1, what you have is your hardware, and then on top of that, you have your hypervisor. And on top of that, you have your virtual machine environments on top of the hypervisor. It's called bare metal because it's directly on top of the hardware. And some examples are listed over here. VMware ESXi, Microsoft Hyper-V, open source KVM, all these are bare metal hypervisors. The other one is type 2 or hosted hypervisor. The diagram for that is you have your hardware, and then on top of that, you will have your host OS, and on top of that, you will have your hypervisor implemented. And on top of that, you will have your VMs. So host OS will sit between the hardware and the hypervisor there. So examples, Oracle VirtualBox and VMware Workstation. All right, let's move on. System calls. Going from a user space to a kernel space, maybe to respond to an interrupt. Let's try to take a look at what are the examples, what are the system calls that are related to the services that are being offered by the operating system. We'll not take a look at all of the system calls, nowhere close. We'll take a look at some of them. Where are they written and how are they written? They are written in C or maybe even down to assembly language. And it is equivalent to a software interrupt. How do you pass parameters to a process? Well, you can do that using registers. You can put those parameters as a block or table in memory, or you can push things on top of a stack and pop them from that particular process. Right? So this is essentially saying you want to do a system call, but you are passing parameters to that system call. Right? So suppose you are trying to create a process. To creating the process, you would have to give it some arguments, some function, arguments to create that process. When you're doing that, maybe you are passing a string, whatever that might be, depending on the system call. Where is that information going? There are three different ways. It could go in registers, it could go in directly in the memory, or managed by a stack. System call written in assembly or a language like C. Types of system calls. There are 6 different categories that are listed over here. This is not a complete list. This is sort of your main functionality of the OS. System calls that are related to process control. Process is what? It is an active program, program under execution. So suppose you want to end or abort a process, that you would have to initiate a system call. So something that needs to be done on behalf of the operating system, and there would be a system call for that. In every OS, it will look slightly different, but its purpose would be to end or abort, to load, execute a process, to create a new process, to terminate a process, wait or signal an event, allocate and free main memory that is associated with that process. So all of these are services that are directly related to a process. And a lot of them can be tracked by information in the process control block, PCB. And we'll talk about that in a little bit more detail. Next, file manipulation. How do you create and delete files? How do you open and close files? Read, write, and seek files, get and set file attributes. So all of that are system calls that are belonging to that particular category, file manipulation. Next, device manipulation. Request and release of a device. Read or write or seek to a particular device controller. Get or set device attributes, logically attaching and detaching a device. All of those things, again, OS has to give you that service, right? You guys see this, my opinion, logically attaching and detaching is probably the most common thing that you see, right? Even if you are not a very passionate programmer, you must have used a USB drive at some point, and before removing it, what do you do? In the OS, you try to click on things that will allow you to safely remove it. When you do that, you don't, okay. I've lost USB drives for that. The memory gets corrupted, man. It's not, there's a reason why it is provided by the OS. So I have lost a good amount of data because of it. And I was not transferring data while I was doing that. It was. So maybe they have sort of, the hardware has caught up to where it is not allowing that to happen anymore. But in the past, it has certainly happened to me where I plugged out a USB drive in a hurry and the memory got corrupted and I was not able to use that USB drive later. Again, I didn't use it. I couldn't use it. Couldn't retrieve the information. And of course, I couldn't save anything else to it. So when you do that, you are essentially logically detaching that particular device. So essentially, what is happening? Every file is getting closed, right? So you had opened the file to write, you're closing that. Next, information maintenance. Example, get or set time, date, system data, process or files, device attributes, all of that going in the information maintenance. Next, communication between what and what. Maybe do processes. So, or it could be between the remote devices over a network. So create and delete a connection. So this is related to like socket programming. Send or receive messages between processes or different sockets. Transfer status information. Attach or detach remote devices. All of these are falling under the category of communications related system calls. Next, set or modify permissions. Protection of files from users. So when you're definitely you would have to do this, right? How many of you have done this? chmod in Unix. Yeah, you have done that, right? You have changed the read write privileges to a certain file. All of that is sort of falling under that last category of protection of files from users, or maybe essentially it's bad users, but it is meant for all users. Let's see. What does a process state diagram look like? Process state diagram is a state diagram that shows you the different states a process goes through. So when you actually create a new process, it is in this new state. It is not currently executing. You just created that new process. Maybe you ran a fork system call and that new process got created. As soon as it gets created, it gets admitted to the ready queue. Ready queue is a queue, essentially a first in, first out. Generally, it is on a first in, first out basis. It could be other criteria, there could be other criteria, but it's a queue of processes that are ready to getting executed, which essentially means that I have loaded you onto the main memory. I just need a processor to work on this process, right? So ready queue is processes that have been loaded onto the main memory. They're ready to go. I just need a process, right? So and who gives it? The scheduler dispatch assigns a processor to that process for it to start getting executed. So you're ready, waiting for a processor. Scheduler dispatch gives you a processor, assigns a processor to you. It goes to the running state. In the running state, well, what is happening? Instructions or operations to service that particular process are getting executed. From the running state, two things can happen. One, you could have an interrupt. Two, you could go into this waiting state, which is essentially a longer wait time. Maybe you are waiting for some input-output operation to complete, or maybe you are waiting for an event to happen. So for example, if a process says, all right, wait for the user to press enter, right? So what are you doing? You're going into that waiting state. So from the running state, you could either go have an interrupt and go back to the ready state, which means again, you are waiting for a processor to work on, to be assigned. Next, from the running state, if you were waiting for some IO to complete or some event to happen, you go to this waiting state, and once that IO or event gets completed, you go back to the ready state, waiting for that processor. But in the ready state, the key is, when you are in the ready state, you have the process loaded in the main memory. So all you're waiting for is the process. It's not like you get the process, then you load things into the main memory. No, that doesn't happen. Ready queue, you already have it ready. A job queue would be something that is all the jobs that are currently active, those are being maintained by a job queue. So things in the job queue, they may not be loaded in the main memory. But if you are in the ready queue, that means that you are already loaded completely in the main memory. Now, from the running state, what can happen? Well, the obvious thing, right? Process can get completed, and then you exit out, go to the terminated state. So the typical way would be what? For very simple processes, new gets ready, gets a processor assigned, goes to a running state, and gets done. Right? That would be your typical straightforward way. Other one would be new to ready, ready to running, and then from here you could sort of do this multiple times, and then maybe you terminate, or you just stay in that loop. So if it is something that is sort of an OS service that is on a continuation, like it's running all the time, then you are just in that loop. Let's see. Next, examples of system calls. We have for each category, like process control all the way down to protection, each of those 6 categories, some of the system calls are being listed over here. So Windows will have its own list, and then Unix system calls are listed on the right column over here. We will be talking about some Unix system calls. So for example, we'll talk about fork, exit, and await system call. We'll also look at how do you open, read, write, close files using those system calls. We will look at pipe, and that's it. So today we'll focus on fork, and depending on time, we may get to the pipe system call as well. Fork is essentially what? Something that will create another process, right? One process has a system call, makes 2 processes, forks into 2. Let's see. So those are just for sort of reference. Go ahead. Oh yeah, absolutely. C code, execute, these are getting executed. Absolutely. And I'll show you examples of a C code, where you use this. Next, process control block. Process control block is per process. All the information that could be associated with a process is in the process control block. In short, PCB. So actually, one thing I would want to include here is the PID, process ID, or process number. After last class, did anybody do this? Look at the processes on their laptop that are currently running. All the PIDs listed, like big numbers, right? You will not see very small numbers, thousands, generally be in the thousands. Let's see. So what does each PCB have for each process? It has the information about the process state. How many states are possible? Well, 1, 2, 3, 4, 5 states are possible. So depending on which state the process is in, that state information is going to be in the process control block. Next, program counter. For a process has a bunch of instructions. I need a pointer to the first instruction, goes in the, or not the first instruction, next instruction to be executed, goes in the program counter. CPU registers, stack pointer, general purpose registers. What are the general purpose registers that are being used for a particular process? Goes in the PCB. That information goes in the PCB. CPU scheduling information. What is that? CPU schedules processes, right? Who gets to run, depending on some criteria. That criteria could be priority. It could be how much work do you still have left, or it could be first in, first out. Whoever comes in first gets the processor first. But whatever that is, that information is also present for that process in the PCB. Next, memory management information. What could that be? For a process, what could the memory management information be? Well, it could be the base and limit registers, right? So process starts here, ends here. That information is also there in the PCB. Accounting information. What is that? How much CPU resource are you using? How much RAM are you using? Goes in there. IO status information. Currently, are you doing some IO data transfer with any device or not? Are you getting information from any device? That information is also in the PCB. And because process state is there, part of the PCB, every time it changes, your PC would get updated. Process ID or process number is an identifier for the process, right? Every process is going to have a unique integer that is sort of their identity. It will be a unique integer. Let's see. So this is for each process block. Each process will have this. Now, how do you keep track of the PCBs? Well, first of all, there are many jobs. There are many queues. You could have a job queue, you could have a ready queue, you could have an IO device queue. Job queue is everything that got admitted, right? So everything that becomes new is in the job queue. Next, ready queue meaning the processes that have been loaded into the main memory waiting for a processor. Those are in the ready queue. Next, IO devices. The processes that are waiting for certain IO devices. Those are going to be in the IO device queue. Now, these queues are generally first in, first out. So there's a head, there's a tail. So for example, a ready queue. Ready queue will have a head and a tail. These are essentially pointers to the next process control block. So if you have, say, the head of this queue, it is pointing to the first control block, PCB number 1. So that could be corresponding to certain process. Say maybe process number 1. But that particular PCB, PCB1, will have a pointer to the next one. And then PCB8 will have a pointer to the next one. And then the tail will have the pointer to the last one, to the head of the queue. So by maintaining this linked list, you are able to keep track of which processors will need to be serviced by, will need that processor. So PCBs go from one queue to another. Job queue, they got admitted. Everything is there. Ready queue, I have loaded things into the main memory, waiting for the processor. Next, maybe I got I'm waiting for an IO to complete. I go to the waiting state. I go to the IO device queue. Now I'm waiting for an IO device. So those are going to go from one queue to the other. Next, process creation, the Unix fork system call. There are lots of sort of things that could be confusing, and I've seen that confusion a few times, and in my opinion, that is sort of unnecessary. So let me go through it in a good amount of detail here so that we understand what is a parent process and what is a child process. So fork is a system call that is used to create processes. But as you can imagine, if I have one process and if I create another one, I'm not really doing something useful, right? I have one job, I've created another job, which is the same as the first job, then it's not useful. What would be useful is, if I have one job, I create another job, and then the new job I can update with something else, right? Different set of tasks in that new job. Then I have two things that are concurrently getting executed. One is doing job one, the other is doing job two, right? So for this, we would need two things. One, a fork system call so that I can create two processes. The other is exec Unix system call so that I can replace the code in one with a completely different executable. We'll take a look at some examples there. So a fork system call is creating a new process. A process executes fork to create a child process. So when you see this fork, that particular system call will be within a process. And that process is called a parent process. When that fork system call gets executed, you have a parent splitting into two. But at the end, you don't have three, which is typically what the confusion is. Parent sort of creates child. That's it. You only have parent and child, right? So think of it as one forking into two, but if you have the total count, it is just two. It's not three. You guys see that? So many times this has sort of been the confusing point. So you don't end up in three processes at the end. You only end up in two. One was the original one in which the fork was there. You only added one more, the child process. Let's see, the original process is called the child parent process. The child is identical to the parent with one exception, that it is return code is different, right? So we should be able to identify which one is the parent, which one is the child. Of course, these are two different processes, which means that their process ID is going to be different. But also, their return code is going to be different. So for example, if you have a parent process that has a particular fork system call at some line, it is going to return a certain value inside the fork. And it is also going to, and because child and parent are clones of each other, it will have a return code for that even in the child. The return codes are different for the parent and the child. So the return code of a fork system call in a child process is 0. That's how you know it's a child process. So if you have a if condition right after the fork, you can check for the return code, whether it's a 0 or not. And if it's a 0, then you can do the work that is related to the child. Next, return code for the parent process is exactly the same as the child process PID, process ID. So you created a child, the child will have a unique process identifier that will be the return code for the fork system call in the parent, right? So the return code is 0 for the child, process ID of the child in the parent. Again, examples follow. Parent and child may concurrently execute. So if you have a processor available for the child, parent and child are concurrently getting executed. But if you have only one processor, then you're sort of switching back and forth. But the option is there for you to execute both processes concurrently. Or you may have a scenario where you are assigning some smaller task for the child and you're letting the child complete while the parent process sort of waits for that child to complete. And again, to wait, there is another system call for that, which is that, wait, or wait PID. A child may duplicate. So if you don't know anything, child is a clone of a parent. But by using exec system call, you can change it to a new program. If you don't do anything, then child and parent are exactly the same. Not too useful. But if you use an exec system call, then you can replace the child process with completely different program. And we'll see an example there. So let's take a look at a logic diagram here, block diagram here that will show you the before and after picture of the fork system call. So suppose there is a process, and I will call this the parent process, right? Because it is what is having the fork system call. So let me call this the parent process. This parent process has a unique integer as its PID, in this case, x, right? So let me just pick x to be 1037. I have just assigned some arbitrary integer to this process, parent process, and its process ID I have assigned it as 1037. Now it's getting executed, right? CPU, it went to the ready queue, got the CPU, it is getting executed. During that execution, it incurs a fork system call, I equals fork. Now, when that fork system call gets executed, the parent process is still there, but you also have now a child process. Well, obviously, there's a question, which is how do you know which one is the parent, which one is the child? Well, the way you know is, you see, process PID is X. It had the same process ID as before. So it is the same process that had the fork system call. So that's the parent. Also, look at the return code. The return code of the fork was going to go in I. What does I have? Y. What is Y? Y is the process ID of the child, right? So if Y is, say, I don't know, 536, right? That is what gets returned over here. So the two ways you know it's a process. One, its process ID is the same as the process ID before the fork system call, so it's the same. The other is it's a non-zero return value, right? If it had a zero return value, like here, then you would know it's a child process. But the child process itself will have its own process ID, right? They're two different things, the process ID and the return value. They're two different things. The return value could be a zero, could be a process ID of the child. If it's zero, you know it's a child. If it's non-zero, you know, well, I shouldn't say non-zero. If it's actually -1, then you know fork could not execute. Question? So how would you create new processes? You would have to launch a new application, right? What if you want this to be taken care of by the process that is getting currently executed? So something like, say you have an application that is running, but it is also doing things that are completely not in your control. So it is doing something by itself. How would you manage that? You would have to do something like this, right? When some event happens, do a fork. And after you do a fork, then you have two things that can concurrently run. While you're doing this job, do also this job. So it is meant for that. But you're right. Usefulness is when you actually replace it with something else. And there's a way to do that by using that exec call. In some scenarios, you may not want to replace it, which is why you just clone it and then you have two things that are running. Does that answer your question? All right, so let's see. So we have the parent process. The process ID of the parent process is not changing. The return value is, however, the process ID of the child. In the child process, so after the fork, what happens? Right, so here, I will just draw a box here to indicate that, right, here you have a box, here you have a box. This guy is, say, child, and this guy is, say, parent. The parent at some line has a fork system call, right? So if its fork system call is over here, right after that, you have the parent and the child, two processes now. But what are they doing? Immediately after the fork, they are executing the next one. So the parent is executing the next line here, and the child is also executing the next line right after the fork system call. Now you can do a check. You can write an if statement in your parent process, right? And that would clone over to the child as well, and you can check for the return value. If the return value is 0, then do the child. And that would copy over here as well, because they are clones. And you know that it is going to be 0 for the child, not 0 for the parent. And that's how you would identify which one is which. Go ahead. They are taking the exact same space in memory. You are absolutely right. Clones of, unless I have an exec system call, they are using the same program, same data, same memory space. Yeah. Did I? Oh, it's here. Unless I implement an exec system call. Next, all right. Let's see this with an example. It'll be a little bit more clear. Now let's talk about transforming the child process. We are going to have to use an exec system call, another Unix system call, to replace the current process with a different executable. So we'll replace the process's memory with a new program. We'll talk about that as well. Another option that you could have after the fork system call is for the parent to wait. So you would have to use the wait system call for that. While the child is getting executed, parent just waits. Doesn't terminate, just waits. Or another option after the fork is a process can kill itself by doing an exit. Kill itself a little bit too strong here, but you guys try to look past that. Or a process can kill, or oh my gosh, why do you have to? Yeah, I think they were running out of the names of these calls. Next, a process could kill or abort another process if it has the privilege to do that. Or after the fork system call, they could just exchange data. Where are you at? Where are you at? Where are you at? Did you complete this step? Did you complete this step? Right? Communication between those processes. Again, there are many ways of communication to be established between processes. Lots of categories, lots of ways to do it. The simplest way of doing it is implementing pipes. Have you guys used pipes? Linux programmer, anyone? Pipes, yeah? Somebody has had to do ls, right? Have you typed ls in a command prompt ever? Come on. All right. So when you do say ls, what does it do? It lists out all the files in the current working directory, right? What if you wanted to find out the list of files in the current working directory with the name, say THE in the file name? How do you do that? Grep, pipe it into grep, yeah. So you would do this, but you would do a pipe, right? So ls, the standard output of ls is being piped into the standard input of grep. What this results in is what? List of all the file names in that current working directory with THE in the file name. That's an ordinary pipe that you have implemented. That was essentially communication between one process and another. ls process, grep another process. That's how you communicated between them. But those are ordinary pipes meant for temporary use, right? Like just temporary. They are not like, oh yeah, it's going to be open for long-term communication where the process is continuously running here, the process is continuously running here. You're writing, reading, reading to ends of the pipe. It's not this. Ordinary pipes are typically short-lived. Oh, short-lived, kill, abort. These are all. All right. Next, before and after. So you had this process, parent process, had a unique identifier, PID, an integer. You had a fork system call in that parent process, forked into two. I shouldn't say forked into two. It created another process, right? So whenever I say forked into two, I think the idea that they are eventually three, that's, I don't want that to happen. So I am just taking one process and making another one. So my parent process is as is, my child process is now created. How do I know it's parent and child? The return code is a non-zero value. The return code is a 0. So this would be a parent, this would be a child. But what if there is no space in the main memory to create a new process? What happens then? You are not able to execute fork because no memory space is not there. Then the return code will be -1 for that. So if your return code is -1, then you know you couldn't create a fork. Oh yeah. So you can keep executing fork, 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 fork. And so homework, coming to that homework. All right, maybe one more homework that I'll assign today. It'll be due Monday of next week. Just one more. It'll be fun. It'll be fun homework. Just counting forks. It'll be counting forks. It'll be very simple. No, you don't want that? No? All right, so let's, really no homework? No, we are talking about like more than 10. Yeah, and then, when you get into child, before you, so if after you do a transformation, after you do the exec, you could have another fork even there. Right. So their return codes are all going to be, so within the child, now it's sort of the second parent, right? The return code within that is going to be a 0 for the child it creates. Next, what do you have? Oh, go ahead. No, it doesn't. So the return value, you would have already set it to 0, right? So that's in I. But when you have another fork inside that, you would say, instead of I, you would say J. J equals some other fork. So the return value is going into wherever you're returning the value of fork to. The only way to keep track of that is by looking at the process, the number of processes that are currently getting executed, or if there is an addition in the PIDs, the list of PIDs. Yeah, that is it. So suppose you are in this child process and you want to replace the code in the child process with something else. Then what do? You execute a ECSE, exec system call in the child. Wait a second, child and parent are the clones, right? So how are you going to differentiate? Right? So child and parent were the same. So how are you going to make sure that this system call is only for the child, it's not there in the parent? Depending on the return, right? So you go through an if condition, check it, and then based on whether it's a child or not, do the exec. So what do? You have this child process. You are implementing a new code, which is essentially passing a path to an executable, right? So suppose you're thinking about a C code. You have compiled it. What do you get? A.out, right? An executable. You could use the path to that particular executable as an argument to your exec system call. So it replaces the current program with that particular executable. Next example. All right. So you have in this example, we'll take a look at how do you do the fork system call, how do you check for the return value, and how do you wait. So you have a main function in here with a integer return data type. Next, you have this particular fork system call. So this is important, right? So here we are storing the return value of the fork in an integer data type called PID. PID is an okay name for this, maybe not the best name for this. The reason is PID is going to be a PID, but only in the parent. In the child, it's going to be a 0. it's not going to be a PID in the child. A better name would be fork value. Fork value equals fork, right? So in any case, you have PID over here. All right, so fork system call has been initiated. Return value is being stored in PID. So right away, as soon as you have that fork system call, you have it in the parent, and parent is going to be there, and now you have the child as well. I'm drawing that in blue. Next, fork has been executed. You've got a parent, you've got the child. Why P? I can just write P and C. Next, what is the parent doing right after fork, and what is the child doing right after fork? Right after fork, parent is trying to execute this guy, and right after fork, child is trying to execute this guy. Right? They are trying to execute the next one. So the parent is going to check if PID equals 0 or not. Well, the return code for the parent was what? The process ID of the child. It is non-zero, right? You guys see that? So the parent is not going to execute this part. The parent is actually going to go into this part because the return value, PID, is going to be process ID of the child, which is non-zero, greater than 0 integer, right? So it's going to go here, execute this. What is it doing? It is saying, checking for, well, PID is not equal to 0, so it's a parent process. It is going and doing some subroutine work. We are calling that do work, which is another subroutine written up over here, to which we are passing this particular string, parent. Right? And after parent does that, it is simply waiting for your child to get completed, waiting for the child to execute. In the meanwhile, what is the child doing? Well, child started executing this. It checked the return code. Yes, the return code of the fork system call in the child process is a 0. So yes, this condition will satisfy and it will start executing the statements here. What are they? Do work subroutine, same work, with the string that is being passed to this child. After that subroutine gets done, successfully exit. After it successfully exits, the wait PID over here, parent was waiting, child completed, now the parent completes, and then you return to the main function with successfully. Go ahead. Oh, the wait PID is essentially the wait PID function is tracking the PID, tracking the process that is passed within their arguments as an argument. So until that process gets completed, it is simply going to just sort of wait. It is still in the main memory. It is sort of not doing anything, but just waiting for it to complete. So by keeping track of the process ID of a process that you're waiting for. Next, right, that's it. So main system call, fork, two things created. One guy did one work, the other guy did some other work, maybe the same work, but the different arguments being passed. And then the other guy waited. Go ahead. This is an example of a system call that would look like. Right. So everything else is sort of my choice. But when I execute this process, the OS is trying to execute that system call. So it's going from the user space to kernel space, allocating memory to it. So all of that is being managed by the OS. But that's the reason why we call it a system call, right? But if condition over there is not a system call, what is a system call? Fork is a system call. Wait PID is a system call. Actually, those are the only two, right? So if you look at a particular a process over here, like a piece of code, this could be user designed or it could be part of the operating system. So it could be either. Go ahead. What is it? Yeah. Exit is also a system call. So successful termination of the program. Exit is also a system call. Yes, you're absolutely right. Right. Those are the ones. Next. Over here we have fork plus exec system call. How are we doing on time? 9 o'clock. Nice. We have a main function over here to which we are passing two arguments. One is the argument count, and another is a vector of string literals. Inside the main function call, we have some PID as an integer data type, two string literals of character data type. Next, we have a fork system call. So as soon as you have your fork system call, you've got the parent, you have got the child, and they're both trying to execute the next instruction. So you do the if, right, to check whether the return value is 0 or not. If the return value is 0, that would indicate that it is a child process. What are you doing? You are making this particular args, your string vector of two string literals, two things. One is a path to a certain executable. The other is a null pointer, right? So you only have one thing there, a path to the executable. Then you implement that particular exec system call with that path to that executable. What happens is the child process, which was a clone of the parent, is now going to be doing whatever is written in that executable. That is for the child. If PID is not equal to 0, then parent process, which is not a really good way to do this, because if it is -1, it's actually no progress, right? Like fork did not happen. So if it is an integer that is greater than 0, then you can say that's a parent process. Over here, we are doing nothing there. We're just doing a printf of not a problem. So parent process is not that exciting. Go ahead. Which one? That is going to be the return value of the exec. So if the return value of the exec, if it successfully happens 0, if it doesn't execute, happens -1. So whether you were able to do that transforming to a new process or not, the return value of that. Whether to check whether the child process got updated with the new code or not. Yeah, go ahead. So different, you're going to find a lot of variations. So it's not exactly exec. Exec is sort of a very common way of knowing that particular system call, but Unix has a lot of variations. So even if you do like a search for exec system call, you will see more variations than exec-v. I'm not 100% aware of all the variations, but it is meant for the same thing. It is meant for transforming that code to a different executable. All right. Even though you guys are ready for the activity, let me use some more time, because we have time, to make progress on our next lecture. So I'm going to talk about communication between processes now. You have your parent or child, or maybe there is no parent-child relationship, whatever it is. You have two processes that want to communicate with each other. So let me spend maybe half an hour talking about the classification. When we return on Thursday, then I will sort of go into a deeper pipe example. And let's see whether we'll get there today or not. So in this one, we'll talk about pipes. The example that we just gave was for an ordinary pipe, ls pipe grep. That was an ordinary pipe. So cooperating processes. What are cooperating processes? What is the counterpart to that? Well, counterpart is independent processes. So if you have independent process, that means that a process cannot be affected or can affect change in the execution of another process, right? Two independent processes. One cannot affect change in the other's execution. So their programs are different. Their memory management, base and limit registers are completely separate, right? And they do not have privileges over the other process. That would be an independent process. A cooperating process, however, can affect or be affected by the execution of another process. This is OR, right? Both don't have to happen. This is OR. So it can affect or it can be affected by another process. So we are talking about cooperating processes in which communication is necessary. Why is it necessary? Well, suppose you have multiple jobs, right? So here, if you guys are all part of a team and you had to coordinate a particular task, right? There's a project. And if you're assigned a project, you would obviously have to communicate with each other to do that project, right? If I said no communication between you guys, but you have to complete that project, that would be absolutely not practical. There's no way you could accomplish that. Why? Because there's no way for you to break it into smaller tasks and then work on them in parallel. You would have to do it. You're imagining your ID team. Yeah. 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 You should do a case study in ID about this, cooperating and independent processes. Right. So the only way we could have subtasks that are making progress in parallel concurrently is if the processes are cooperating with each other, if they are passing messages between each other. Now, there are different ways of doing this message passing. One way is I will send you a letter to a mailbox and you open the mailbox and read it. That is called typical message passing, and the mailbox is part of the kernel. The other way of doing it is shared memory. I will write something to the memory and you read it from the same location from the memory. I'll give you the address, you just read it from that address. So that's called a shared memory approach to inter-process communication, two of them. But we'll talk about more about those things. So what are the advantages of process cooperation? Well, we can use this to share information, maybe shared access to a shared file. Computation speed up, exactly what we said. Project, you guys are all doing it. You all want to make progress so that the task can be completed faster. And the only way to do it is break up the main task into smaller tasks, and then you guys communicate with each other about who is doing what subtask and how much progress you have made at each step. So computation speed up. We can also do a modularity and reuse, right? Why is that? I have taken processes and I've broken it down. Once I've broken it down to meaningful subtasks, then only then I could have assigned it to different people or different processors. So it increases your modularity and reuse. And also its convenience for multitasking. They are all sort of related to the one example that we said. The information sharing requires communication mechanism. Processes need to know, so maybe this is the initiating process. They want to know the status of where the other process is, maybe the child. What do? They pass information, they pass messages. Where are you at? The child process would tell the parent process, all right, this is my status. So this is sort of keeping track of overall progress of that subtask, but it is not limited to just finding out the status, right? It could be, all right, you worked on something useful, this is your result, I will give it back to you so that you can use it to do some other tasks. Inter-process communication between two processes. Here you have process P, process C. Well, I'm using P and C here. The P and C is not limited to just parent-child. It is, in fact, for producer-consumer. Think of it as any process, some process P and C. You establish a link between the communication processes so that IPC can be carried out. Right? That link will be the mechanism because of which that communication gets carried out. P should be able to send message to C, C should be able to send message to P. So it can be unidirectional communication, it can be bidirectional communication, and if it is bidirectional, it can be half duplex or full duplex. You guys know the difference between half duplex, full duplex? Yeah, go ahead. Yes, so when you're doing half duplex, you're only sending or you're only receiving. Only one thing can happen at any given time. But when you're doing full duplex, you're sending and receiving at the same time. Unidirectional bidirection is very, very straightforward, so I'm not going to talk about that. What are we going to do with those communication links? We are going to use send and receive primitives These are system calls that are going to allow us to exchange data between two processes. So send, then you need an identifier to know which process you are sending that message to, followed by the message identifier, right? So this is your process ID that identifies who are you sending it to, and then the message, not the direct message, but an identifier to that message. Next, receive. Process ID. Wait a second. How does it know what the message is? How do you does this make sense to you guys? Send, okay, send to this particular process with this message. But then receive, you have already received the message. How does that work? Nice. Exactly. So that's a message identifier. It's not the message, right? So whatever that message is, it will be stored in that particular identifier, right? So that's where the message identifier is going. It's not the message. All right. Next, many OS-specific variations exist. Like I was saying about the exec, there will be variations to these system calls. Next. So two approaches to inter-process communication. One is shared memory, and the other is message passing. Can you guys tell me which one is which? Let me use. All right, this is good, and this is good, and this is good. Shared memory. This is the other one. Message passing. Message passing works if the messages are small, right? Shared memory, good option for large files, but also those are possible only when there is a shared memory between the processes, right? What if the processes are not having access to the same shared memory? Then you cannot do that. Then you would have to resort to the message passing approach. So what is message passing? You have process A and you have process B. Two processes that are trying to communicate with each other. How are they doing that? Process A is sending a message to a mailbox or a port, and through the kernel that is being relayed to process B. So this is message passing approach relies on mailboxes or ports. But the problem here is that kernel is involved. So it is slower than the shared memory approach because there is a context switch that needs to happen. User space to kernel space, back to user space. Go ahead. Which one? This guy? Oh, just the kernel. That the kernel is not involved. Over here, the kernel is involved. The kernel over here is not involved. So in the message passing approach, process A is writing to a port through the kernel, and that same mailbox identifier has to be used. Process B is reading that mailbox. So, oh no, just processes, like different processes. I think the blue, gray, like it's just alternating colors. Next, in the shared memory approach, you actually have to, so the initiating process has to give up some of its space. So if process A says, I want to send message to process B, then it has to allocate some shared memory space within its own memory space. That's for process A. So it creates, there's some space that gets allocated to the shared memory space, and process A will write to it using the send primitive. And then process B will read to it. Now process B, of course, will need to have read privileges for that amount of shared memory. But process A needs to allocate that. Kernel is not involved, so no context switch involved. You're always in the user space. So faster. Problem over here is what? You need a shared memory, right? So you need the what if the computers are processes are connected through a network? Then that is not going to be possible because there's no shared memory there. So not a good solution for distributed systems. Distributed systems, you use message passing. For small messages, you use message passing. So messages pass. So here we have the differences between the two approaches. On the left, message passing. On the right, you have shared memory. So message passed between the processes through the kernel. So context switch involved. It is much simpler because there's no memory sharing going on. There's no shared memory, but it is typically used because of that presence of kernel. It would take a long time, and it is reserved for smaller amounts of data. It's a good solution for distributed systems because distributed systems don't have shared memory. And within this message passing approach, you have direct and indirect message passing approaches, like a classification within message passing. In direct approach, each process names the other, explicitly naming the processes that are involved in the communication. In indirect, you talk about mailboxes or ports. So in indirect, you're not hard coding things, right? When you do direct, then you have to hard code things because you're naming the process, which is not a best way of dealing with things. If you are a programmer, you know hard coding things is not a good thing to do, right? Everybody agrees, right? We agree on two things. One, don't hard code things, and the second is what? Comment your code. Yeah. So in direct approach, you are explicitly talking about which processes that are involved in the communication. So may not be the best solution always, but it sometimes you might have to do that if those are the only two processes that are involved in that communication. Always. Indirection is better because you can just change the mailbox. You don't have to worry about anything. So that's your message passing approach. Shared memory approach is the other one. Messages are exchanged to the shared region of memory within the space of the initiating process. Much faster because kernel is not involved, context switch is not necessary. Used for large amounts of data because you can have that shared memory to be longer. A can write all that data to it, B can read from it. Shared memory is usually in the memory space of the initiating process, like process A, who was trying to send message to process B, like we talked about. Now, with this shared memory, what do you have? You have a limited space in the memory. What you could have is a producer-consumer problem, which is based on bounded versus unbounded buffer. What does bounded buffer mean? Well, there's some limitation to the buffer size. Unbounded means there's no limitation on the buffer size. If you think about a producer-consumer problem, for example, you have a web server sending information to a web client, say a web browser client. So you have a producer in the server and you have the consumer in the client. In that, if you have a buffer in the middle where you are storing information that is being sent by the server, you could have that buffer to be bounded or unbounded. Suppose it is unbounded. Right now, you guys must be feeling like, oh, wow, this is the best news ever. Unbounded buffer, right? Because no limitation on the buffer size. The server can just keep sending messages. I'll put it in the buffer, right? There's a problem. There's actually a big problem there. What is that? If the consumer wants to look at the most recently sent item, it will have to remove all the items that came before that, right? So even though it's a good news that unbounded buffer is there's no limitation. It's going to be non-blocking for the sender. Sender can just keep sending messages. But the receiver, if it wants the most recently sent item, then it has to look at or remove all the other things from the buffer out to look at the most recently item, which could take a very, very long time. So that's the disadvantage there. But with the bounded buffer, we also have a problem. The problem is what? If there is nothing in the buffer, then the consumer is waiting for some things to happen, right? So the consumer is just waiting there for the sender to send, the producer to produce. If the buffer is empty, if the buffer is full, what is happening? The sender is saying, I need to, the sender has to block, right? The sender has to block if the buffer is full. The consumer has to wait when the buffer is empty. So in both cases, you have a limitation on when they can send or receive. So what you do is you try to get the best of both worlds. You should have a reasonably large buffer size, but it has to have some limitations. Because if you don't, then to get the most recent item, you are going to be waiting for a very long time. So that's sort of the bounded versus unbounded buffer. This is the classic problem with producer-consumer problems. So that is going to be for the shared memory, because shared memory is that limited size which is being used to pass messages from one process to the other. Next, message passing. Details about message passing, then we'll talk about details about shared memory. Message passing approach, which is what pipe system call is. Pipe system call is a message passing approach to IPC. If process P and Q wish to communicate with each other, the operating system must offer a communication link. And that communication link is being used to send and receive messages using that send and receive primitives. These are both system calls that fall under the category of communications that we said, right? Communications between processes. This communication that falls under the category of message passing could be direct versus indirect. Explicitly name the processes versus don't do it explicitly, just talk about the mailboxes or the port numbers. Or it could be synchronous or asynchronous. Synchronous or asynchronous is essentially blocking versus non-blocking. Blocking and non-blocking are exactly that, has to block or no block. We'll talk about that classification as well. So let's talk about message passing using direct communication. So here we are explicitly naming the processes. So processes must name each other explicitly. Look at this. Send to process P, explicitly mentioned, followed by the message identifier. So what is P and Q here? Let me just. So this is process IDs of the processes that are communicating. Right. So you've got the two process IDs, and then we have got these two messages. So let me underline, do that. And these are message identifiers. So send this particular message to process P, receive a message from process Q. Message identifier is the message. So whatever message you get, you put that message in the message identifier message. So send a message to process P, receive a message from process Q. Next, properties of these communication links. Links are being established by the operating system. A link, so as these system calls are getting executed, the operating system is essentially establishing that link. A link is associated with exactly one pair of communicating processes. We have explicitly named those processes that are doing this. Between each pair, there exists only one link. So as you're doing this send receive, only one link is existing between them. Links may be unidirectional, but they are usually bidirectional. So once a link gets established using direct communication mode of message passing, they can be unidirectional, but they're typically bidirectional. So that send and receive can be other way as well. Send Q and receive P. So here we are doing that hard coding, explicitly talking about the P and the Q, the process IDs of the processes that are trying to communicate. In the other one, in indirection, there's a mailbox that you send message to and receive message from. So there's no talk about which process is trying to communicate. You just send a message to a mailbox, you receive it from the mailbox or the port. So each mailbox has a unique ID. So using that unique ID, you send that message to that mailbox and receive it from that mailbox. A link may be associated with many processes now, because any process can send a message to that mailbox and any number of processes can read from it. Each pair may share several communication links because of this. Again, links can be unidirectional or bidirectional. So all that is there is the mailbox unique ID. That's the only thing that is involved over here. And as you may imagine, you don't do big amounts of data with this, right? Like you can do it for smaller messages. For big amounts of data, you would reserve that for shared memory approach. Next, indirection. What are the operations that are involved? Well, one, you would need to create the mailbox. Another system call for that. You would send and receive messages through that mailbox. And once the communication is done, you destroy that mailbox. What are the primitives that are involved? Send and receive again. Send. What is A here? A will be the mailbox unique ID, right? So mailbox unique ID, same for both of them. And then the message identifier. The message identifier that talks about which message you are sending. This is message identifier will be the identifier to which the message will go. But A in this case will be your mailbox unique ID. And then the other two are your message identifiers. Next, synchronization. So we talked about message passing, direct versus indirect, two modes. And you could also have synchronous versus asynchronous, also called as blocking versus non-blocking. So whether there it is direct or indirect, message passing can be either blocking or non-blocking. Blocking is considered to be synchronous. What is that? Within blocking, again, there are two processes that are involved. One is sending, other is receiving. So within blocking mode, you could have blocking send or blocking receive. What is a blocking send? Blocking send means a sender blocks or waits until the message is received. I will not send you more messages until the consumer or the client says, I have received that message. That's a blocking send. Blocking receive is what? Receiver blocks until a message is available. Until the producer, until the sender sends a message, I'm going to block. When the sender sends messages, I'm not going to block, receive the message. And as soon as I receive the message and there's no more messages to receive, I'm going to block again. So that's a blocking send versus blocking receive. But over here, it is also called synchronous. Why is that? Now they have to be in sync, right? The sender and the receiver, the producer and consumer have to be in sync because of this blocking nature for send and receive. Next, non-blocking or asynchronous. Non-blocking send is you just keep sending. Don't worry about whether I receive them or not. That's a non-blocking send. Non-blocking receive is receiver receives a valid message or it may not receive any message, which means null. Right? So there's no constraint over when you can receive and when you can send. That means asynchronous. So non-blocking method is asynchronous, considered to be asynchronous. Blocking is considered to be synchronous. Next, buffering. So in the message passing approach, you can have buffers that can be of zero capacity or bounded capacity or unbounded capacity, right? Implemented in one of three ways. Because messages are residing in temporary queues. Those queues are buffers implemented in three ways. One is zero capacity. Zero capacity is no capacity at all, zero messages. What does that mean for send and receive? Sender must wait for receiver. There's no capacity for that queue. So whatever you send has to be delivered, only then the next message can be sent. There is no space for me to store any more messages that are being sent. So in this case, both the send and receive are blocking. Bounded capacity, which means now the queues have certain limit, finite length of n messages. So in this case, sender must wait if the queue is full. If the buffer is full, the sender must wait. The sender must block until the space is available for it to create more messages, right? To send more messages, because messages are going to be in the queues. If there is no space for messages, new messages, then the sender must block. Sender must wait. Unbounded capacity, no length of the queue. The sender can keep sending, and the receiver will keep receiving. No limits. on when that can happen. But we also talked about the problem with this, right? Infinite capacity buffer has a big problem, which it may not seem very severe, but in real world application, that's a very big problem, where you have this particular buffer that is full, and if you want to look at the most recent item, you have only one choice: throw away everything else that came before that, which could be loss of data, right? Because you are going to have to do that same communication again. So unbounded capacity is not a practical solution. A bounded capacity is what is a practical solution. Because on the other hand, if you go too bounded, right, like zero capacity, what happens then? Again, there is a problem, because the sender will only be able to do one message at a time, right? So there's no place for it to buffer. So on either end, you have a problem. Only the bounded capacity is sort of your happy medium. Next, pipes. What are pipes? Well, it's a channel to allow processes to communicate with each other. Ordinary pipes are there. They are named pipes. What are the issues that are related to the pipes? Well, one question is the communication between one process to the other process going to be unidirectional or bidirectional? Well, again, it depends on type of pipe. Is it an ordinary pipe or is it a named pipe? Next, by the way, what we created, ls pipe grep, it was a ordinary pipe. We didn't name the pipe, we just used it. Next, question that is related to the pipe. Is it a half duplex communication or is it full duplex communication between in case it is 2A, then is it half duplex or full duplex? For processes to communicate with each other, is it required for a parent-child relationship to exist, or there is no such criteria? So for example, for ordinary pipes, you have to have that parent-child relationship. For named pipes, no such relationship needs to be there. Next, can the pipes be accessed over a network? That depends on whether you are using the message passing approach or shared memory approach. Pipes are message passing approach, which is essentially over distributed systems. So they support communication between devices that are connected over a network. Next, ordinary pipes are inaccessible from outside the process that created it. Typically, a parent process creates a pipe and then it uses it to communicate with the child process. So idea is parent process will have this particular pipe Unix system call. A pipe will be created. There will be two ends to the pipe, a read end and a write end. Parent will be writing to one end. It doesn't have to be that way, but parent will write to one end and then the child will read from the other end. In fact, the process that communication could also be bidirectional. So a child could write to the right end and then parent could read it from the read end. There are two ends. So you would have file descriptors to distinguish between which end is the right end of a pipe and which end is the read end of the pipe. Named pipes are pipes in which you're actually naming the pipe. It is for a longer duration of time, right? Ordinary pipes are temporary, like for a very short duration. But for a named pipe, you're naming the pipe, and there's no such parent-child relationship that needs to exist between the communicating processes. Next, talk about ordinary pipes. I'm going to stop in a couple of slides, and then when we come back, we'll do the example. So ordinary pipes, standard producer-consumer problem, which is what? Producer cannot produce more than the capacity, and the consumer has to empty out that buffer, right? That's a producer-consumer style problem. Essentially, consumer is waiting if the buffer is empty, and the producer is waiting if the buffer is full. That's a producer-style problem. Producer writes to one end, the right end of the pipe, and then the consumer is going to read from the read end of the pipe. This ordinary pipe, which is for temporary purposes, requires a parent-child relationship between the communicating processes. So let's take a look at this, right? There's a pipe. It has two ends. You have a parent process on one side, and you have a child process that is indicated on the other side. both processes are actually reading and writing in this particular diagram. So when you have this fork system call, sorry, not fork, pipe system call, that pipe is created, and you would have to have file descriptors 0 and 1, two file descriptors, one for reading and one for writing. So file descriptor 0 is actually used for reading, fd0 and fd1. This you use for reading from a pipe, and this you use for writing to a pipe. Let's take a look. Parent process uses fd0 to write to read from the pipe, and child uses fd0 to read from the pipe. So what I know is this end is the read end. Maybe not the best choice. That end is the read end of the pipe. Now, parent uses its file descriptor 1 to write to this end, and child uses fd1 to write to this end. So that is your right end of the pipe. So in this case, both parent and child are able to write and read to the pipe. So it's a unidirectional link that gets established. However, if you do not need a particular process one-way communication, you only want one way, right? So you want only the parent to send messages to the child. Then what you can do is you can close out the right end of the child. Go ahead. No, it's just there's no other reason, no good reason. It's just pointing to that end. Yeah, no good reason there. Example of a ordinary pipe. List all the files in the current directory. Standard output of that is being piped to the standard input of grep. So all the file names with Apple in it. That standard output is being piped into more. Give me all the details, right? So when you execute this particular line, what do you get? You get all the details of all the files in the current directory with Apple in its file name. So those are ordinary pipes, temporary purposes. Named pipes. Named pipes are more powerful than ordinary pipes, more long-lasting. No parent-child relationship is necessary. Communication is bidirectional. Several processes can use this named pipe, right? So pipe is there. Many processes can access that. It is provided on both Unix and Windows systems. We'll be taking a look at ordinary pipes for our example. We'll not be naming them. Next. All right, let me stop here. And when we come back, we will try to, well, let's just finish it. You guys are okay with hanging me for another 20 minutes, right? Let's just get it done. So message passing using Unix pipe system call. You're okay, or take a break? Take a break? It's okay. We just have a couple of slides. I don't think we are, as soon as this shows me 5 slides. All right, let's just stop. We have made enough progress. Let's stop recording here.